He's chased all the way out here from Sacramento. He's a fabulous teacher. What else was I going to make up? Speaker at conferences, well-renowned. Have you written any books?
I just keep getting asked.
You just get
Riley to write a book.
Okay, so he's been asked. So fabulous information. We know that you're a wonderful speaker, and we're going to learn templates.
Maybe.
Maybe?
Learn something. Yeah.
Maybe. Cool. Begin.
All right. So I just finished teaching a 2-day C++ course in Silicon Valley a couple hours ago. So we're hoping my voice holds out here, and my energy level also holds out.
There's a mic if you need it.
Thank you. I typically don't, but I might actually need that. Okay, so we're going to talk about template metaprogramming, and we're going to do it in an informal way. If you want to see some more formal type stuff, you can look up my name on YouTube. It's there. I work with Ciere Consulting. We teach courses about once a month or so, but that's because we're passionate about C++ and we want to teach other people about the language. Primarily what we do is we solve hard problems for people using C++. The people who work at Ciere are authors of Boost libraries and maintainers of Boost libraries, people who deal with that type of thing. We do a lot of library design, and we're really pretty passionate about libraries should have amazing interfaces for users to use. And one of the ways that we achieve that is through template metaprogramming. So let me ask the question right off the bat. How many people in the audience do metaprogramming or have done metaprogramming? Okay, so there are a few that know what this is and what we're going to be doing. I'm going to start off by giving at least a few different examples here of just call them motivations. What we might have for why we might want metaprogramming as a thing. And we're just going to look at some applications that exist. The first one is BoostDash. So BoostDash, who knows what BoostDash is? I should have brought my shirts. How many of you raised your hand and have a shirt? You don't have a shirt? Okay. I need your name, because you knew what BoostDash was. That was amazing. So BoostDash is a template.
I saw the video.
Oh, you saw the video? Which video did you see? The one from CPPCon video on BoostDash. All right. Was it okay? I haven't watched it yet.
Yeah.
Good answer. Yeah. You definitely get a shirt. I just need a name. Okay. So BoostDash is a template engine in the vein of template engines like the Webby guys think, right? Where you've got some text that's going to describe what you're going to output and some data AST, and you apply the two together, and the output is some magical new output. So Mustache is one, Django has one built in, Handlebars, there's all these different types that are flying around. And BoostDash started off as this project during BoostCon or C++ Now, depending upon what you want to call it, where we write a library in a week. And so we never succeed, but we came pretty close with this library. And at the end of the week, we had things somewhat put together here. And the idea is that we have some input, the template bit, and we want things to get replaced. So like, we're going to use mustache format, double handlebars, or double curlies like that mean. That's the replacement. So that will be name, and that will be age. And I'm going to create this data. And data is of a map, this map T type, which is a map, an STD map of string versus string. Okay? So very simple thing. I can initialize one, and now I have one. Name, Yaroon, and age, he's 42. I aged you. You like that?
I noticed.
All right, so I have one. That's my data set. And that's my template, where now I'm going to try to apply the two of these things together. This is the interface for BoostDash. I need the iterator, the begin iterator, and I pass that to load template, giving it the begin and the end iterators for the template. I instantiate it with the type. I'm dealing with mustache type as opposed to like a Django type or what it is. This is actually going to compile the bits for me, and now I have actually this compiled template thing. And the next set is I'm going to generate. So I give it a stream where I want to generate the output to, the compiled template, and then the data. And this is what we want to think about at the moment. There's a lot of template metaprogramming that's occurred in order to get all of this stuff done I recommend you actually maybe watch the BoostDash video if you're interested in it. Data right now is this. And one of the design criteria, the thing that we wanted for an elegant interface with BoostDash, was we wanted the user to be able to determine what the data type was. It couldn't be like Michael's idea of what JSON data is. It couldn't be just like some simple string-to-string mapping, because that is horrid. It's not going to be what this library thinks or something else. I want anything that you choose, user-defined abstract syntax tree, data types, to be able to go in there and just somehow magically work. So for something to magically work like that, it's got to figure some things out. Like here we have now, this is the input. We don't really care about it right now. Some invoice items. And invoice items, if we look up at the top, we've got a map of strings to strings. That's an item. And we have an item list, which is a vector of items. And we have an invoice, which is a map of strings to item lists. So we have a map in which we've got a string. And what's on the other side? A list, or a vector, of a map of strings versus strings. So I've kind of got now this funny hierarchy thing, right, that I've built. And I want to be able to just pass that in. I've created this invoice items thing right here, which is an item list. I've got one. And now I have an invoice in which lines has been assigned this mess of stuff. And I should be able to just like load my template as normal and pass that in as the data without doing anything else, right? Anything special. How about this one? Now I have an extended variant. A Spirit extended variant makes, who knows what boost variant is? So it kind of makes like boost variant into an object. What is a variant? Well, the variant can hold one of these types. The variant can be either a string or an object or a list. What is an object type? An object type is a map of a string to a value type. Oops, this value t. And what is a list? It's a vector. So this is interesting. This is now a recursive data structure that I've described. And I want to be able to generate one of them. So now this is going to describe my invoice. And I want to be able just to pass that into generate right again. And now, somehow at compile time, this has to figure out what this data type is and how to deal with it, how to generate the right bits in code in order to descend it. Well, what types of things do template engines do? We looked at the one, right, this was super easy, when we were just like getting Jeroen's name and his age. This one's a little more complicated. It has the invoice number that's going to go at the top. It's got some information about a company that's going to go in here. It has these lines, so it's going to iterate over however many lines there are, looking up item codes, descriptions, and amounts. So this has some concept of a list, and it's got some concepts of looking things up. Okay, that's not good enough, though. We want to be able to take, like, an author. And what is this author type? Well, the author type is just some struct. And I want to be able to pass that in without any problem. So this one, we're going to play a little trick here. We're going to actually use fusion adaptation, and we're going to adapt that struct to, in essence, to have a definition of what it works out to be is a tuple of references to the types. And then we can get super crazy because most of us have like invoices that have invoice numbers. It's got a type, it's got a company, some complex thing, and it's got lines, and just be able to pass that in. All right, so here's another example of craziness. Who uses Spirit? That's the same people that just keep raising your hand. And the ones that on this side of the room either have worked for me, or are friends. And I don't know who the other ones are. So we need to talk later. I want to know who you guys are. So Spirit implements a parsing grammar. It's a domain-specific embedded language. Hi, Richard. So the idea is that we have this domain-specific embedded language that is a parsing language. And at the top, that's kind of the peg grammar for an email. We're going to ignore all of the errors with the grammar. Like, for example, I only care about comms, orgs, and nets, and things like that. But we can get away with it. It says that a name is, A through Z, one or more of those, followed by a dot, and an A through Z, one or more of those, and there are 0 or more of those things. And so, you know, you can look at that peg grammar, it's like an EB and F or whatever, and now if you blur your eyes a little bit, this grammar down here, which is spirit, kind of looks the same. We can't put the plus sign in the back because, well, there are rules to our language. So we have an operator that we're going to use. And this is saying that there are going to be 1 or more characters A through Z followed by 0 or more, dot followed by 1 or more characters A through Z. And we can compose those things together. Eventually an email is a name followed by an @ and a host. I can read this, and thanks to wonderful expression templates and template metaprogramming, this will produce a grammar for me. Not only will it produce a grammar for me, but it does really cool, amazing things. So here I have a grammar, and this one, I'm going to say that this grammar, this alpha followed by 0 or more alphanumerics, this thing is going to synthesize, is the word we use with grammars, it's going to synthesize an STD string. And this one down here, this rule down here, the quoted one, it's going to synthesize an STD string. And this one, which is a name followed by a colon and either a quote or a name, this is going to synthesize a pair of strings. And at the end, when I finally parse all this stuff through, when I actually do it, I'm taking this item thing, which was names followed by a colon and quote or name, and I have a list of these things. And what am I saying I'm going to put it into? This key value map. Key value map, which is just a normal map. And I'm telling Spirit, you're going to synthesize this into a map. Well, it ends up that these could be any containers at all. Any containers that can, like, store things or have pairs of things. And at the time of compilation, we have to run some type of program that's going to take care of forming all of the code that we need at that moment. That's what metaprogramming is about. So metaprograms run basically at compilation time. Here's another one. Boost MSM users, any? The same. Oh, I got another one on this side. Okay, so metastate machine, it's part of Boost. It is blazing, screaming fast, what it produces for a state machine. And one of the cool things about it is it uses template metaprogramming so that we can write state tables like this. This is the start state. This is the state I'm in. This is the event that might occur. This is the destination state. This is the action that will be performed. This is a guard condition that I might want to check. That's super easy to read. How many of you have like homegrown state machines that are that easy to read? Yeah, you've got one. How many of you got? Let's just start with that. How many of you got homegrown state machines? Like lots of people have homegrown state machines, right? But I bet nobody or few. I wouldn't say nobody. Nobody has a table that's as easy to read as this one.
Okay.
This is generated at compile time. Okay, so this is being utilized inside of Laden, which is a distributed state machine model at the basic level locally. If you have two of these distributed state machines, you can make them communicate to each other because they have ports, and those ports have input signals and output signals. And if you're familiar with real-time object-oriented modeling from way back in the 90s, which eventually became UML real-time stuff, those were called actors back then. And they are a lot like actors today, but not quite. So one of the neat things about these state machines that are distributed about is that they have these ports where they communicate out. They have a defined set of signals and data that they can send and that they can receive. So this is the protocol definition within Laden that we can use in a port. The end signals are in that first list. Get pressure, stats, get shield, get side. These are the out ones. Pressure, stats, shield, message. Now if I hook up two ports, I bind those two ports together between two state machines, when I send a message, so at compile time, I have bound these two state machines together. I say these are attached. They're talking. They're going to talk to each other. When I send a message, it would be really nice to know that the message that I'm sending to that state machine is a message that that state machine port on the other end can receive and know something to do with, right? So basically, the message that I'm sending is an end message that it can receive. And if I can do that, then at compile time, I can find all these little errors of, oh, I'm receiving crud that I didn't mean to get, and I don't know how to handle because machine doesn't know what to do with it, right? Well, that's something that I could test then at compile time. So here are some different ideas of why you might want to use metaprogramming. So let's do this. This is either going to be a horrible idea or just a mildly horrible idea. And I'm not sure which yet. So we'll use the word live coding. Some live coding is going to happen here. So Jeff and I work together, and Jeff knows that I've had weeks of sleeplessness plus now training for the last 2 days. This may be really horrible, by the way.
Or funny.
It could be funny, definitely funny. I hear you guys are a fun crowd, so it'll be good.
We're very funny.
So let's do a little bit of metaprogramming. We're going to just start simple, and then we'll build on that. And one of the fun things about metaprogramming is you don't actually ever have to run anything. You just have to compile stuff. I worked on a project for about 1.5 years where there was never an a.out that I actually ran. For 1.5 years, all I did was try to induce errors in the compiler so that it would spew out stack, so I could figure out why whatever didn't work, right? So there are tools that help out with metaprogramming. You act surprised. You should know that there are tools. Of course. Can you think of any tools to use? Have you been to any of Abel's talks?
Oh my goodness. Myers class.
All right. Well, there are tools that you can use to help with metaprogramming. You should use them. I'll talk to you, Richard. It'll be great. Let's start off with something super easy. What is this? Oh, that is a typo. What is that? That was a quiz. Yep. Make pair. What does make pair do?
Makes a pair.
Makes a pair. All right. And sometimes we call these proxies, right? Because they're going to help us out in getting a job done. We can't just create a pair or a tuple and let the class deduce the types. That's not possible. But we can get the types deduced as arguments to a function call. And we're going to use that because we're basically lazy, which is why we went into the field that we're in now, as opposed to some other honest field. And so let's write make pair. What does make pair take for the two arguments?
Two stuff.
How about we just say T1 and T2? We won't argue about names for now. I know, it's not fun. I'm not fun. Okay, so we're going to take in these two guys. So I probably need to write the word template here, right? And so we've got, ooh, wow, this is going to be interesting. All right. Now, what is the return type of this? What am I going to return? What? Okay. I want to return an STD pair. And it's going to be an STD pair of? Okay. You're smiling.
You could have returned out a trick question, but I think we've already passed the point where the trick is.
Okay. What's the trick question?
Well, you don't really want to take them by copy. You want to take them by reference of some sort.
All right. So let's just continue around with the track we're on, and then we'll fix it. Does that sound good?
Sure.
Yeah. All right.
Keep smiling though.
Yeah, and you keep smiling over there. Thank you, Arthur. It's weird coming out here and knowing everybody. There's so many of you. You're mostly friendly people. All right. So we can do this, and we'd be wrong, by the way. But this is like, ooh, this is.
It's definitely wrong.
Okay, we could write that, and like conceptually, as we think about this problem, we can start thinking about, this is what we want makePair to do. We're going to call makePair, and I'm going to get some value out. So makePair, and I should probably get a pair out, right? Now, there are some problems right away. Let's work with the first one. The first thing is I probably don't want to actually take by value. In fact, I want to take this by something else. This is also a trick question, and if you answer it wrong, I might yell at you, by the way. Okay, what is this?
A forwarding reference?
Oh my goodness, thank you, Richard. All right, so ampersand, ampersand, when these are template parameters, this is forwarding references, right? So this is going to give us perfect forwarding. This is not a reference. There's somebody who writes books who calls these universal references. He's wrong. There is nothing about this that's a reference, okay? This is going to let me take whatever came in and move it along as the exact type. How many of you have dealt with problems where you've got CV qualified, const, volatile qualified things coming in, and you now need to write the overloads for all the const, the volatile, the R reference versions, the L reference versions, right? You're like, this is stupid. Why did I pick this career? And so you've got, now you use Boost preprocessor to produce them for you. That's eventually what you do. You fall back on that. And then you realize, okay, I actually needed 2 arguments, or I need 3 arguments, and this thing keeps exploding. Perfect forwarding solves this problem for us. And so now I can just do this, and bam. Oh, wow. You know, what's the problem is I'm just not used to typing that way, with my head backwards behind me. All right, so now I end up carrying through exactly what I wanted for the type that came in. So whatever the type that came in was, that's going to be forwarded along to the pair. Great, now, now my life is almost complete. So what else, when I look at this, is going to maybe be troublesome?
Constraints or reference types.
All right, so the next thing that's troublesome is the type that comes in is actually not the type that the pair is supposed to be, right? All right, how many people here know what decay is? That's more people than raised their hands so far, except for the ones that wanted to go to a Christmas party or something. All right, so decay is what happens to an argument, right? In normal terms, and we need our types to be decayed, and it just so happens that somebody already has written a decay for us, so we're going to use that one, at least at the moment, because that will make it easier. So there is, we'll just say like the V1 type. And we can't write using again, because that would be stupid. And we're going to decay. Now, let's pretend like we don't know what we're doing, and let's do it this way. We're going to decay the type of T1, and we're going to take the type. All right, is everybody familiar with the using instead of type defs, right? Okay, so this is our alias, using aliases. Now, using aliases are really cool, and there's already an alias for type name, type blah for decay, and they're for most of them, and we can actually just do this because we don't like typing. So there we go, right? And now we've got our 2 types for decay. Don't mess with that one, it was perfectly fine. All right, and now my type has changed, and I'm lazy, become a Python programmer anyhow. So now we've got this, all right? Okay, things are getting better. Let's talk about decay a little bit, because decay is something that's making some decisions and having to do things at compile time. What is it doing? Any idea? All right.
Removing references. Removing references?
Oh, okay. So one thing is it's got to remove reference. Let's no longer use the std decay because they know what we're doing and we're going to pretend like we do. And let's write our own. Because Richard came up with it, it's Richard's decay, our decay. Infinity. All right, so how these things work, the original one that we wrote down here, we had let's write it. We write things like this. This is the canonical way to get a type. What this is doing, this meta program is going to calculate a new type for me. It's going to determine a new type at compile time. : I'm going to get the type out. Type name is here because the type is a dependent type that's dependent upon T2. So I got to tell the compiler, any good two-phase compiler that you might use, there's one that isn't one, by the way, that that this is going to be a type that comes out. So up here, eventually, what I need to yank out of my own decay that I'm going to write is type, right? It's going to be some type. So Richard's right. One of the things that we have to do is we have to remove the reference. That's one of the things, but it's actually just one of the things. So we're going to say using, and we'll just come up with a new name, and you guys like you earlier, you, and there are all kinds of type traits. There are already meta programs that exist that you can just use. And type trait things are just meta programs. So let's go ahead and use one. Oh my goodness. So remove reference. We're going to give it T, and we're going to get the type out. All right, are we okay? All right, so if T had a reference, then this is going to get rid of it. So let's talk about what does that do. What do you think remove ref is? Remove reference. In fact, this will be fun. We'll make it Richard's. RR reference. I'll never make it for typing. There we go. All right, Richard? So this is going to be a template thing again, and RR ref. Excellent. Good job. Okay, so we're going to have one of these, and let's make one. So the first version of it is going to take a T. So we're going to specialize this. And it's going to get a T, and its type inside is nothing more than T.
You have to remove the template.
Thank
type
you.
Name and specialize it. Wait, no. Well,
Look at that. So
Yeah, that's not.
don't mess with me, okay? I'm way undercaffeinated.
yeah.
Yeah, okay, there we go. So this one we specialized for T, and this one we specialized for a T reference. And the type is just T. I've stripped the ref off.
Right.
So this whole concept of RR ref, or removing the reference, is nothing more than a specialization, and do that. So how many of you use templates on a regular basis? That was more people. Oh, wow. Okay. So, there are really like two ways that people approach templates. Templates are like the preprocessor replacement thing on steroids. That's like the one way people use templates. The other way is people realize that the template engine in C++ is a pattern matching engine. And once you come to that conclusion and you understand that it does pattern matching for you, you realize I can write declarative programs, which is kind of what we just did. This is just pattern matching, right? It is going to take and match the T with the reference versus just the plain old normal T. And it's going to get the one that's the best match for me. And if I start thinking about the template engine as a pattern matching thing, then I can solve all kinds of other problems by using the template engine and instantiating things. So, all right, we got rid of our reference and we used our very own reference removal technique. That's pretty cool. All right, one of the other things we have to take care of is if the type T is an array, like brackety array,
Style array.
then we have to do,
Turn it into a pointer.
we have to turn it into a pointer. So, this could go on all day and we'll never finish and get to go eat, so we won't do that.
We have to strip off constant null, right?
Yep.
Yep.
All right, we're going to use this conditional thing. So there are all kinds of things that are built in. Notice I've been just writing std : I haven't been writing boost : mpl : because the type traits inside of C++ 11 provide almost all the things that I want. And between the things that are in 11 and the things that are in 14, I don't need a lot of stuff. We'll see in a moment something about like type lists, like how to get a type list and convert it maybe into a variant. Maybe we'll try that in a minute because that's super easy. Things that used to be very hard and difficult to do, which is why we had NPL, the Boost NPL library, have become easy because either they're built into the STD or because we're going to find that there's just some more power that we didn't have before. Oh, you know what? Here's actually, talking about power, okay, this RR-ref thing, it's okay, but it kind of sucks. So let's do this. Oh boy, type name. Yeah, I guess we probably should do it that way. That makes everybody happy because it's consistent. Thank you. So this is really fun. This alias allows me then to go ahead and use RR-ref-T as if I typed in type name, ref, blah, 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 : type. So this might seem like small syntactical sugar, but every time you write metaprogram junk, you have to write type name, blah, 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 : type. And that's like noise in trying to understand the problem that you're solving, right? So this is a big deal for helping out with metaprogramming and getting rid of all of this crud. Oh boy. Okay. So that's how those things work. That's pretty easy, right? Like that. In fact, let's use the conditional T version too. Now, conditional is going to take 3 template arguments. The first one will be evaluated for its Booleanness, its value of being true or false. And if it is true, then this type will result in the next type. And if it's false, it will result in the third argument's type. So I can say something like, is array, and we're now using u. Okay, so I could do that.
Oh wait, that colon value looks ugly.
Okay, so that colon value does look ugly, but we have to do one of two things. You're right. The colon, how many of you are using a C++ 17 enabled compiler yet? I win. All right. And because it looks ugly and I'm using a 17 compiler, I can write that. And if I'm not writing a 17 compiler and I don't actually tell Chandler,
No.
what?
No.
What do you mean no?
Since when are you in the standards committee?
I'll
I'm not, just show up.
I authorize this.
Chandler wouldn't agree with this.
When will there be operator overloading for metaprogramming?
When will there be operator overloading?
For metaprogramming?
Yeah, what?
So you wouldn't need to say std : conditional t, you just say using type equals boolean question mark type : type.
Well, we can't overload question mark for anything at the moment, so it's available
For something.
for types.
Yeah, you should go to the
Only
next committee
overload
meeting.
types.
It's in Jacksonville. That's it.
Hawaii.
Also, it's not a pet name, it's a context for bool.
Oh, it is. Sorry. Oh my goodness. Woo!
This is a tough grad.
Wow. Yeah, but this is even more cool in some crazy way, right?
You've taught Emacs C++ 11. How nice.
So if you were using 17, you could actually do what I'm about ready to write, but I haven't written yet.
Yep.
Oh,
Yeah, we're getting there. All right.
Nearly.
Okay, we're not going to worry about spelling errors anymore because we just won't finish, and you guys know what we mean. All right. There. Perfect. So that's a constant expression. Bool. It will evaluate this thing. It's that same aliasing type thing that we saw, but now instead of being a type, it's the value, right, that's being deduced. That's cool. Yeah, you're not supposed to do that. It will be in 17. I don't think anybody will care. So if it is an array, if the thing that comes back is an array, then we have to do something about it. And, well, we can, because
Extends.
extent
Yeah. D, I think.
of u.
Yes. Oh no, it is a T. No, never mind. We're good.
All right.
No.
But then you have to add.
You have to add the pointer back in. So you
No,
need
I'm getting
the
there.
type pointer at the end.
Oh, yeah. Yeah. And I can do it just right there. There, we're good. All right. It's just a little ugly. Oh my goodness. Stop arguing with me. All right. So what has just happened is this condition will test true if the thing that I have is an array, like square bracket array thingy, right? What does that look like? We're not going to write it, but what would that look like? Well, that would look like, over here where we did the ref thing, except that there are going to be two overloads. There's going to be one which is the empty like this, and there's going to be one that has some ordinal in it like that. Those are the two overrides that are going to return true, and everything else is just going to return false. Make sense? So that's just, easy type traits. Again, just pattern matching. That's all this stuff does. Pattern matching. It's easy. Okay, and then if it isn't one of these, if it's not an array, then it must be something else, right? And the something else we have to worry about keep getting nested. Is it a function? If what I have is a function, then I need to add a pointer to it. And if it's not a function, then what do I have? Something else, and then I have to remove the CV qualifier. Okay? So we'll just say is function. I'm just trying to get the idea. U. Then we're going to use the add pointer.
Right, can't we just say U star actually?
Stop. Could we say U star?
I mean, we do above, so it seems
Yeah.
better.
That's almost readable.
Not really.
I think that's why it bothers me. Is can't function that's bothering me. Talking about bothering me. Okay, and then otherwise, it's remove CV type of U. All right, now we're finally done. So this was what's all inside of the decay. This is Richard's version of it. It probably works, Richard. Probably fine. I'm sure it'll come out. This type of a meta program is pretty basic in the sense of it's using type traits to match things and make determinations of what the final type is that I want, and then I can extract that type. Okay, so that's make pair. Let's talk now about another thing. It's probably not really what I meant to do at all. Okay, it works. All right. Who knows what a boost variant is? Excellent. All right. So boost variants are like unions, right? Except that they can hold any of these other types. And they're very clever and cool because you can write static visitors for them, where you write a visitor, which is just overload of the callable operator for all the types that could possibly be in the visitor. And then you can apply the visitor that you have, of which type you have no idea what's on the inside, right? You apply it with the visitor, and the right thing gets called, and it makes for some really, really fun stuff. Now, what happens a lot in generic programming is we'll have a list of things. For example, in the Laden library, all the possible signals that could get sent around for that port, it takes all the possible ones that could be sent to that port, and it just makes a variant type that can hold any of those types. So now it has a variant type that can hold any of the signal types that can possibly move through the port, and it can use that internally for moving it around to the state machine. All right? So at compile time, it's got to figure out how to make one of these. Well, if you remember right, we had two lists. We had the in list and the out list. And we're going to need to take the in list and the out list and combine those things together and take out duplicates, because I don't want like ints showing up twice, the same data type showing up twice. Like maybe my in signal was ping and I have an out signal ping. I don't want ping to show up twice. I want the variant to have only one of those types that it deals with. And eventually now I have a list. We're going to ignore all that other part, though. With C++ 14, it's actually really easy to do. So, but we're going to ignore all of it. And we're going to say, at some point I have a list of types. In metaprogramming, we deal with a list of types a lot. And it's like the people in the standards committee suddenly liked the people who wrote metaprograms for just a short little bit. And they started giving us some things. And one of the things that they gave us was the ability to have variadic templates. Now, they didn't like us a lot because parameter packs are mostly useless. But they're not completely useless. So at the moment, this thing called meta list up here, I could specialize it if I made one of these. I could specialize it with an int, right? Okay, and I could make another one that took a float. Now, those are two unique types. This is a type meta list that is parameterized with an int, and a meta list that's parameterized with a float. Those are different types in my system. All right. How would I make this a variadic template? Well,
Dots.
we like dots. So the dots, 3 dots before the type declares the parameter pack. And dots after the type expand the parameter pack. Let's just start with getting one. Now I should be able to write whatever I want here. I have a list of types. Now, one thing to think about with metaprogramming, if you've not done it before, types are what exist at compile time. They only exist at compile time. They're all over the place. They're wonderful. We love types. Types are what we're going to use and process and do everything with. And we're going to take types and compose types to make new types so that we can make decisions to make more types and eventually some more types. The other thing that we can work with are integral values. We're not going to worry about integral values right now. We're just going to worry about some types. So one of the things I need to be able to describe when I'm doing metaprogramming is I need to be able to describe a list of types, a type list. And in MPL and other things, there are type lists, varying types of type lists. And they're not like this under the hood because they're complicated and hard, and we didn't have a way to do this before. Now we have this way to do it with the ... And this says I can have however many I want. There's a perfect list now of types right there. So I have that list of types. That's pretty cool. I want to take that list of types and I want to make the list of types into a variant. So if I'm going to make a boost variant, I would list the different types here. Float, string. All right, so I have now my variant is a variant of these things, right? So if I just need to figure out how to take my list up there, that meta list, and make it into a variant. So let's write a meta function, and let's call it as variant. And the reality is we're going to probably do something like this. And I need one of these, right? All right, so what this is going to do is I should be able to use this in such a way that I can say, instead of this, the equivalent will be able to be as variant ML. I should, this, I want to become one of these things somehow. I want to take a type list and convert it into a variant. All right, so what is going to be this as variant impl? I bet you can guess.
So specialization of that meta list of ... t and then passing to boost variant t ...
Woo! Let's do your idea. It was good. So I'm going to have some struct in which it is this as variant impl. And if you recall inside here, we're going to use type because that is the canonical way to deal with getting types out. And it will be,
Here it doesn't.
oops, not, excuse me. Right, there. Okay, we're going to have one. Getting ahead of myself. And I'm going to specialize it.
No.
I am, actually. And because it's so cool that I can just make right shift operators really be ends of things, I'm going to shove them all next to each other. Oh, shoot. Don't hit that. Actually, let's make it a little more legible there. Okay. So what this is saying is I've got this as variant impl, right? It is templatized on some type. And I'm going to specialize it on my meta list such that the type is some parameter pack, some number of things coming in, so that I can get them back out. That's the expansion of it. So, by the way, how you want to think of variadic templates and the expansion of it, the thing ... is this side, in this case with the T, the compiler replacing it with its very own name, comma, its own name, comma, its own name. You can put all kinds of wacky code, well, it's not there, but somewhere else. You know, in here when I expanded it, I could expand it like with some big lambda expression, blah blah blah, whatever, another ... and it will take that and like parser-wise, put a comma and then replicate it again and put a comma and replicate it again. Anywhere that you can have a comma-separated list of something or another's, that's where you put these expansions. All right, so what is my type in here?
Boost variant.
Like that?
Yep.
Yeah.
So I just wrote a meta function that takes my type list and converts it into a variant. Let's talk about how this works. So, right here's my alias, so that I can take care of the type name for the dependent type, and it's going to yank the type out. L is the list that it's specialized on. The specialization of as variant is going to take that MPL list, and it's saying that whatever this MPL list thing is, it is a template parameter, but I don't want to deal with template parameters. We don't want to write this in some generic way. We could write it in a generic way where we just work with tuples, by the way, or anything, but that's going to be some more syntax right in there that might be ugly. We can actually do that maybe in a second. But this is my meta list, and whatever the expansion pack is of all the types there. So I already have them. And here then, I can just expand them out. So this meta program that we just wrote, Bryce has written a lot of meta programs. Bryce, if you had to write this in 03, what would it require?
Put me in the spot here. A lot more work.
A lot more work. A lot more work. Arthur, do you have an idea of what it might require?
8 years.
8 years. Arthur's answer is in years. You would have to do a lot of work to recursively instantiate new things that took the type that came in and added it to another type, and then created another one and recursed down until you finally got like way down there at the bottom and you got the full type back out and you used that. And it would have been ugly, and it would have also taken more time to compile. And we can almost, whether you've done metaprogramming or not, you can almost reason about what's going on here. It's not so bad. It's not horrible anymore. Yeah? Jeroen says it's not even horrible anymore, so we must be good. So, all right, so that's my as variant example. What do you think it would take to combine two list. So remember, I have one list. I've got this list. Actually, let's just do one. If I have a meta list, or I have a meta list, don't I? Why make another one? What did we call it? ML. Okay, so I've got this meta list of all these things. If I have this meta list and I want to write a meta program that allows me to push front.
Zipper. You want
Push
a zipper?
front.
Which one is zipper?
Not yet. I want to push front.
Oh, I want zipper.
What's that?
Concat.
Concat.
Okay.
Okay. I want to concat. I give it my current list and some new type. I want to add on that int at the end.
Okay.
Okay? And whatever that type is, that's my new type coming out. All right? So actually, what would a concat look like? What would be inside here? So it's probably and it's going to be called concat, and it's going to be a specialization. We won't worry about all that right now. But the first thing is going to be this meta list, what we did before, right? It's going to be one of those. And this is going to be my new type that came in. I'm going to change it because I don't want to think about the other one. I'm operating on too little sleep at the moment. All right, we'll do front because this will be easier. No, you're right, they are equally easy. No, it was fine the way it was. Stop messing it up. Come on, guys.
Sorry.
Oh. All right, so in here now we have our new type. This is our canonical way to say that we're going to do this. It's a meta list. And what is the meta list contain of?
Comma U.
Wow! We just wrote a meta function that will take the list and concat another list. That's pretty awesome. Now, it's also kind of boring in the sense that wouldn't it be fun if this was actually able to take another meta list of U types? Okay, that's 4 is special. I can't tell you what that one does. So now I can take 2 of these lists and now concatenate them, and I have a list, right, that I can deal with, a single list. So one of the things that we do often with lists of types is we want to find, like we want to remove all the integral types out. We want to make a new list. Well, I have now a way to concat, right? So if I could iterate through that list of types, which actually isn't so hard, if I want to iterate over a set of things,
Can you just try to a recursive pattern saying struct remove duplicates meta list t dot 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 comma u comma t2 dot 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 comma u comma t3 dot dot dot.
okay,
Oh, we could.
yeah. That's actually, yeah, that's close.
Can you just start with an empty list and concatenate if it's not
Can
same?
it be empty? Can these dot dot dots be empty?
I don't think that can be deduced.
They're types.
If you do is not same and you start with an empty list and you concat from an empty list and do it like that, very list be a new, but yes.
It's not a regex mention.
You understand what I'm saying? You start with an empty list. And
Yeah, start with an empty list and we just keep adding on.
You can't, yeah, if not same.
If not same.
Yes.
Yeah, so we could do that with the same thing, right?
Yeah,
in this one, we're just going to try to like strip out all the ints or whatever it is. But we need to move through one of these things, right? And how do we move through one of them? Well, we write the specialization. We're just going to write foo at the moment. We write the specialization, so it's something like this.
Yeah.
Where this is going to strip out the first one of our parameter pack, and now we've got everything else that was in the parameter pack. So we can deal with this, right? And then, well, we could write the meta function to test whether this matches what we want and concatenate it on something else that we didn't pass in yet, but we would. And eventually, what a parameter pack can have how many elements in it? The end part is interesting, but less interesting than the lower bound. What is the lower bound?
You can have none.
It could have none. So this could become very dangerous very fast.
Lower bound is M.
The compiler eventually will say something like, the sky is not large enough to hold the program you wrote, or something like that. So you don't have the haiku mode turned on? You should, because it's awesome. Chris, I'll laugh. Do you not know that with the old Apple compilers back before? Oh.
Oh,
What is
remember
this?
that.
Okay. Well, this is like dinner time conversation.
Okay. Lighthouse.
All right. So eventually we need one of these to terminate when we start recursing over and over again, because we're gonna end. What I want to try to point out here, there's no way that in an hour we're going to actually teach you anything about metaprogramming. If you came in thinking that, I'm sorry. but you started to see some of what metaprogramming is. Metaprogramming all occurs at compile time. These are programs that are going to run at compile time to help us do our jobs. As a result, your compile times are long. But the compiler is very smart, and none of this ends up inside of your final generated code, except for the things that you generate that you want in your generated code. And it's very good at collapsing things along the way. Using metaprograms is basically a way of exposing a lot of information to the compiler. And when the compiler has a lot of information exposed to it, it's able to optimize just like the bejeebies out of it. If you start wrapping things behind virtual functions, it's stuck. It can do nothing at all. Which is, by the way, if you don't need runtime polymorphism and you wanted polymorphism, you probably want compile time. Most people do. They don't want runtime. You should use compile time polymorphism because it's going to be fast in comparison to the runtime polymorphism. You want to try to do as much as possible at compile time and expose things to the compiler. All right. So here is kind of like, since we're out of time, this is like your introduction here to some metaprogramming things. Are we out of time?
No, you got like at least a half an hour.
You're kidding me. I thought there was like an hour.
Anytime you need a beer.
This kind of ends when.
It ends whenever I want it to?
We'll probably leave
When
by midnight.
people start leaving, it ends.
At that point, it...
Well, if there's one
I could
here.
be here for a while.
I mean, Tide House stops serving food when? 11?
Yeah,
I'm
11.
hungry,
Yeah,
so.
we're usually the last to leave.
Hmm.
Actually, I think it ends when you need to leave, when our lovely semantic representative leaves.
You got time.
You might be tired.
Well, he'll snooze.
I'm
No.
tired. Okay, let me ask this question. How many have seen, because I almost hate to ask this, how many have seen or were in my talk on modern C++ techniques? I've given it like a whole bunch of different times.
We had to be more specific.
Yeah.
There's only one. It's 3 hours long. Well, sometimes it's like 2 days long if you hire me. But if you don't hire me and you got the cheap version, you watch it on YouTube. Okay, so let me recommend that you take a look at that. It's called Modern C++ Techniques. So, like, how many of you like modern rock? Nobody. One.
What about 30 Rock?
So, look, modern rock is stuff that was like came out in 1980. It's not what we necessarily call modern anymore, but the tag goes along with it. It's still what we call modern rock. It came out in the 80s. Modern C++ is not what Microsoft says it is. There's a book already written about modern C++. Andre wrote it, and it talks about techniques that, in essence, became metaprogramming later. It's the introduction to all of that, right? It's ageless, that term. It doesn't mean your C++ 11 compiler. It means this way of thinking and programming. So if you look up the stuff on modern techniques on YouTube, there is at least one, if not two versions of that. And it goes through and talks about all these different ways that you can use declarative programming techniques in order to solve problems, because that's a lot easier to think about and to deal with. But it does it in an O3 point of view. And so as you go through it, you're like, oh, that was a whole lot of work in order to finally get that final answer. If you watch that, you can then apply a couple of these techniques and realize and appreciate how quickly you could write now meta programs. Those same problems that we were trying to solve at the time, super easy to solve now. Let's do one more. That's slightly. Okay, so if you've seen the BoostDash talk, you can leave now. That was very sad. Jeroen's making fun of me up in the front right now because I'm kind of new to the Mac world. I've drank almost all the Kool-Aid. As far as I can tell, I drink all of it. There's nothing left. My pocketbook says so. And I'm still failing. It's like I want something to move this other thing over. Oh, really? Once you make them full screen, they're kind of stuck. Yay! Oh, something, I don't know how it works. That's not it. I'm using the wrong program.
Yeah. Well, no, you're looking for how to make it full screen?
I just want it big.
Yeah, I think that's the up arrow next to the magnifying glass. Or that.
Slideshow. It's a different program that I brought up the first time, so now I'm really stuck.
So it's great.
Oops. Okay, so we talked, from the motivating examples was BoostDash and how you can take in all of these crazy different things and somehow they all work. Where are we at? Nope. A little bit further. Okay, there we go. So, BoostDash has some abstract syntax tree that it creates. That abstract syntax tree represents the template that got read in and compiled into some recursive variant type is really what it is. So that describes the abstract syntax tree. That's it over there. And based upon the engine walking this abstract syntax tree, as it walks along, it's basically interpreting in a VM, in a virtual machine, what to do with these instructions it has. And the instructions that it gets, it has to now go and get data and do whatever's associated with it. So if the instruction is look up name, it's got to go now to the data AST and figure out what name is and pull name out and do something with it. So here we go. We don't want to deal with that. We want to deal with the context. So that's called the context. And this is the user thing that got passed in, some data type. I don't know anything about it. I'm not sure entirely what it is, but I've got to be able to do some things with it. And it comes in just as some template parameter, whatever it is. And I'm going to need to generate against the template that I have and the context, that data that got passed in, and wherever I am inside that data from the user. Okay. So one of the things that we can do is we can test, and we can also render output. We can also iterate. Oops.
I think because it's in slideshow, it's periodically going one slide ahead. So if you just keep hitting back every time you do that, it'll be okay.
Really? That is ridiculous. Is that a Mac thing?
So
Yeah, that's what I thought. This is why Jeroen told me just to use skim. Just use skim.
Or don't use an app.
Or don't use a map? Is that what you said?
Yeah.
It's starting to get
I don't know, runs the next grade.
You know, the hardware is really impressive, which is why I got the machine. I've been cursing the fact that they call this a Unix, though, ever since I got it. Oh, okay, okay. Is that normal that it does that? What is it skipping?
And then the phone screen doing yours. Yeah, when you click on it, you click slideshow instead of present or whatever the appropriate thing is. I'm sure it has a non-slideshow.
I don't know. I've been teaching with this one for days. I know this one works. Okay. So one of the things, if you remember, one of the commands was this for each. I need to be able to cycle through things. And the user has passed in some data. I don't know what the data is. Let's just say it was our map. A map of string to string. That was like our first example, right? That's what got passed in. So if I have this for each, I've got the stream that I'm outputting to. Node is like the instruction set where I'm at. Context is the type of the data that the user's passed in at the point that I'm at. I might have like already been floating around in their AST. But it's where I am at the moment. And now I've got this thing called the for each category. So if you think about it, I can go ahead and iterate over anything that lets me do that, right? That the user gives me. I could iterate over a map, I could iterate over a list, I could iterate over actually a tuple if I wanted to, of types. I could do all kinds of things if the user's giving me this thing to be able to go over it and look at the different values that are inside there. So this category is important. This for each category works out to be, it's going to take the context in, the context type, it's a meta function, and it's going to try to determine what is the category of the thing that it has. And we deal with classifications of things in categories. So we do this all the time in Ciere, as well as in all kinds of things in Boost, like Spirit. Spirit deals with categorizing things so it can understand what to do with them. Is this type that I'm synthesizing, is it a type that's a container type and I can do stuff with it and act like it's a container? And I just treat all containers the same. So we're not real great with names at times, but you know, we have an unused attribute, it's a plain attribute type, a sequence, associative, tuple attribute, a variant, and an optional. So
So if I'm understanding this is tag dispatch, but these are tag types like the iterator tags in the standard library.
But different. So we're going to do tag dispatching, which means that I'm going to get a type, and based upon the type, I'm going to make a function call that is going to be using that type, or dispatch based upon an overload, a specialization of that type. We're going to write our own. And the reason that we're going to write our own is because these attributes have different terminology based upon what I'm doing. As an example, if I'm in my virtual machine in the instruction set where I'm trying to do a for each over something, well, what can I for each over? Well, I can for each over a tuple.
But not in the same way that you could for each over a vector.
But not in the same way that I could for each over a vector. But if I had a tuple, I know that this is a thing that I could treat as if it's something that I can for each over. And so in the for each world of categories, a tuple, as far as I'm concerned, is something that I can deal with iterating over. As well as I want to maybe treat the map in that case. Do I want to treat the map as something I can iterate over, or do I want to treat the map as something that is associative? Well, actually, it works out that most people don't want you to iterate over their maps. They want you to use them as associative things. So I don't want to deal with that, right? The map is special. It's not an iterative thing that I'm going to be able to move over. So that's where we are there. So now for each just needs to take care of this tag dispatching all the different types that might exist. So, okay, so here's the for each category. So to start off with, the for each category is just some plain attribute. That works for me. And then the for each category here, if I have a T and the T is a variant type, then this is a variant. And if it is a sequence and not a map, well, then I'm going to treat it as a sequence. This is how I get my associative. So here I want to treat maps of strings to T's as associative things, because that's what users like. There's a way to specialize all this better.
Another question, clarification. MPL identity is just a library thing that just has an nested type, def named type.
Yeah. So the reason that MPL identity is up there is because what kills you in compile time is instantiations, and this wraps it in a level so that it doesn't instantiate it, and I get to use the type. I don't want it to be instantiating things all day long, so I use the identity. Okay, so I called generate. This is the for each does nothing more than calls generate in the normal case. But here, when it is a variant attribute, so here's a place to stop. When you do tag dispatching, the normal way most people think about doing tag dispatching is you have actually created a specialization of a structure in which your tag dispatch is what you're going to pull out, and then you're going to call some static function inside, like apply. The other way to do it is you overload one of your arguments with whatever the type is. And so now we're just doing argument overloading, and that means we don't have to instantiate more types, and so that's faster. This is a faster way to do what we need. So when I call for each and it's just this variant attribute, what is a variant? Well, I don't know, right? It's something important on the inside, but I don't know what it is yet. So I have to unwrap it. So I'm going to unwrap the variant and call for each again after I unwrap it. So if the user has given me whatever the user type is a variant type, I need to unwrap it so I can get to what the inside of this thing is, because it might be actually something useful, like a container. What does unwrap look like? Well, unwrap this is the apply visitor, where it gives it the visitor and it gives it the variant. It's going to do nothing more than call for each with the unwrapped version. So now whatever's inside the variant is going to get called. Now for each comes, and we're going to call for each again. Well, what if it's an optional? If it's optional, we're going to figure out whether I actually have one or not. Because if I have one, then I need to dereference it and get the thing out of it and use that, and then call for each with the dereferenced version of the optional. Eventually, we're going to get to a sequence, and we can do range base 4 of whatever the user passed in, whatever that type was, and generate that. Okay, so as your eyes are glazing over and you're looking about going to that brownie in the next part, what just happened that you might have missed is the user has supplied some data type. And it looks like we're dealing with a bunch of runtime things, but all of this has to be generated at compile time. At compile time, it is descending the data types and trying to figure out what can happen and how to deal with them. At compile time, it's generating all the right calls for all the data types that might be in the user's AST. For example, if I had a variant that's a recursive variant of containers to that same container to a container to a container, this just figured out how to descend all the containers in order to get to something that I can deal with at compile time. This is how the magic inside of of BoostDash works in order to deal with whatever data type that the user might give. We categorize things, and in this case, for the instruction of a for each, we categorize what we want to do with for eaches. For testing something, one of the things you can do inside of the template languages, you can test like Booleanness. Is this thing true? Well, what is truthfulness for a container? Truthfulness for a container type is, do you have anything in it? For an associated type, it's, do you have the key? For a value, you probably just want to test the value. And so the virtual machine, based upon what the category is, applies the different types. Okay, so that was some more meta-programming without actually realizing that we were doing meta-programming in a sense. These run at compile time. Again, they're programs that are running at compile time and they're generating code for us. This is actually generating a little more like real touchy-feely code as opposed to the other code, which was very ethereal. You'll never see it. Yes?
I have a question that I'm not sure if this is a welcome question or not, but okay, so it's generating all the code for everything I can possibly pass in. Like I give it a vector of ints, obviously it generates code to handle vector of ints and also ints, because my iterator for vector of ints, I need to handle ints. So, like, that makes sense.
Only if your AST has a vector of int, right?
The thing that I actually pass in, if my context at some point is vector of int.
Yeah.
And if it's like variant, it'll generate code to handle all the different kinds of things in variant. What if I pass it a boost any?
Yeah,
What does it do?
That's a great question. It doesn't actually know how to deal with a boost any. There's no category for handling a boost any right now. So it would break. But there is an extension mechanism for it. And I thought I had a slide. Here is the slide. That's for render. Well, here's an example for render. If you have a type, right, your very own type, you just made it up, there's no way that the thing can figure out the category, or you want it to be treated differently, inside of BoostDash extension, you would write, for example, how do I test the truthfulness of this thing, of whether it's there or not, or how do I render it? In this case, what we were doing is we were writing one for functions. So any null array function that gets called could be part of our AST that got passed in, and it would get executed, and the result then would be returned. So comes in here. We're going to actually execute our function, right? So if you had a boost any, here you would actually, this would be boost any. How do you want to deal with the boost any for test? How do you want to deal with the boost any for the render? And once you figured out how you want to deal with it, you pass it back into calling render, and then all the magic again happens for you, right? So it's like a way of escaping out, adding this extension to handle your very special data type, and then you recall render or test or for each. You recall that with the thing that you've got, or generate, which is the very, very top level, and then magic will happen for you again, and you don't have to write all that other stuff. So that's how you deal with boosting. It would be very platform specific, or excuse me, application specific. Are you asking more hard questions?
No.
Good, because that guy in the corner over there looks really hungry.
I agree.
Yeah, all right. Phew. Thanks,
Would you
Richard.
like
Do I want to be done?
you want to be done?
I want to be done. Can I be
Okay.
done? Sure. All right, so I thank you guys for coming. It's nice hanging out with you. I promise the next time I come that I'll be like more together. We won't do live coding. I don't think the live coding thing worked. I think that was kind of a bad
That was
idea.
fun. I like it.
Really? You thought it was fun?
That was cool.
Okay, all right, well,
There you go.
if I come back and I do live coding again, it's his fault.
Please come join us at the Tide
I had
House.
a question.
We'd really love to have you come and hang out with us. If you have a job you're looking for, make sure you speak to people.
It was a